So our project is called Best Life.
I'm Ashton Harkin. I'm from Lakewood, Colorado. I'm Luke. I'm from Colorado Springs.
I'm Elena. I'm from Cape Coral, Florida.
I'm Emma Park. I'm from Lewisburg, Florida. Mining rescue is a specialized emergency response used to save miners trapped or injured underground. When we were given this situation, we began to research the possible problem. We found multiple resources describing how the equipment were carried by both the rescue and team and miners were having. This led to a problem statement. We understood the various responsibilities of the rescue team, and we sought to ease the transport of materials underground to increase the efficiency of the rescue mission.
So for all the ideas, we start with a design similar to Wall-E that's able to go across rocky terrain in the mines. It also will carry high weight items for the rescue team, such as how Wall-E carries different items. So in our solution, we came up with a removable roof so that the rescue team can quickly grab out all the stuff they need that's packed inside the robot. This allows it to lessen the load of the weight for the rescue team, as it normally has to carry hundreds of pounds, which is really difficult for them. The robot is driven by the fresh airbase so that they can have extra information of how the mine looks, and they can actually visibly see the mines or the rescue team before. And then we came up with the acronym BEST Buddy. BEST stands for Bed, Emergency, Storage, and Thermal.
The length of the Best Buddy is 5 feet 6 inches long when the stretcher is open, and 5 feet when it is closed. And the Best Buddy is supposed to be 3 feet tall, and it is supposed to be 2 feet wide with the flaps closed and 3 feet wide with the flaps open, which each flap is going to be around 6 inches long. This prototype is not to scale. The FLIR is a forward-facing infrared. It is a thermal camera that allows the fresh air base to guide the mine rescue team through thick smoke. And then we have a LiDAR system, a light detection and ranging, which allows them to navigate the team through dangerous hazards when smoke is not visible. There is a camera which allows the fresh air crew to view the mine through the camera and allow them to guide the team further through the cave. Then there's a high lumen flashlight that allows the mine rescue team to see, because the Best Buddy is going to be leading them through the mine. And the neck has wires connecting it upward through the neck to power the power inside of the head, which is like the LiDAR, the FLIR, camera, and flashlight. And then we also have an extension cord which will be attached to the back of the neck to power the battery while going into the cave. It would be around 200 feet long that disconnects and would be reeled back by the fresh air crew to preserve the batteries.
For the tires, we decided on shark wheels, since they are made for different surfaces. It's perfect to go through rough cave grounds. The pedals are the main reasons for this, because they expand and contract kind of like eagle wings, making them very flexible to go through different rough surfaces. The stretcher design can be used for carrying the injured and also to make any necessary treatments. The fabric and straps are made to make sure that the injured doesn't fall out of the robot. And then we made sure to accommodate different size and made the stretcher open in both the sides and the end. And in case of emergency, the stretcher is removed.
For the storage, we had the idea of easing the weight load for the rescue team, and to do so, we've implemented slanted slopes to carry oxygen tanks and medkits, whatever the robot has. And if the items were vertical or horizontal, they'd be too big, so that's why we adapted with slanted slopes. But the first compartment of the robot is the mechanical compartment, which includes all of the batteries, wires, everything the robot needs to move around in the cave. The second compartment is the oxygen tanks, which is extra oxygen for the rescue team or to bring oxygen to the patients. The final compartment is the medical compartment. It has medical kits, bandages, whatever they need to treat the patient.
Simple inspiration we created a Best Buddy. There are modifications made, such as size, orientation, and safety components. We recognize that this equipment will be costly, but we believe in prioritizing saving lives over worrying about costs. Overall, we learned how to design and create something that would be applicable for real life problems and would and hopefully reduce casualties and increase the speed and rescue processes. Thank you.
Are there any questions? Yes.
In your designing, working as a team, or just what challenges did you face and how did you?
Some challenges we faced were trying to figure out how the head could move on its own. And so we overcame that by designing a ball joint system with a 3D printer, which allows the head to move independently, which would be accurate to the design. It was also hard to scale it down to make it, well, a prototype that we could use. So we just we had a base design and we scaled it down enough so that it would be able to be built in the short amount of time we had, and just make it look like we want it to as the Wally design. Yes.
So if I remember, yeah, you said that the length when the flap is open is 5 feet 6 inches. So how would this potentially accommodate someone who's maybe like taller than that, maybe like 6'4"? How would that work?
So we tried to make it at least 5 feet 6 inches long because it's going to be narrow inside of a cave. And so we had to make it like about an average human size. And so if a person is 6 feet tall or is taller than that, their feet would have to hang off the edge, but they would still be strapped to the device, the bed, like this. It would still be strapped to the bed. And so that would allow for them to be transported out. So their feet wouldn't be on the ground, it'd be still extended forward. So their feet wouldn't be dragging on the floor, but it would not accommodate someone who's 6 feet, but they would still fit. Yes.
When constructing this, what's the areas do you have in mind for its use? I mean, it can't be used for every scenario,
Yes.
fires, collapse, and stuff like that. Do you have a dream scenario making sweeper before?
Yes, I remember in the mine, there was a very tall ladder. Say if someone fell off of that ladder and say broke their leg and they were alone, this would be a good device for them to be transported out with a mine rescue team. Because if if there was like hazardous gas above, there would be a the gas man who would detect what the gas is. And if that person is okay, this would be an easy transportation method out of the mine for that. I'd feel like broken bones, someone getting lost even with like the LiDAR system, stuff like that would be a perfect scenario for our robot.
I'd like to add that if the mine was really smoky, maybe the team couldn't see very clearly, the thermal will allow the robot to easily point out the individual that's needing assistance.
Is there any more questions? Yes.
So what if the individual will further spine? I know that you can't really move them there so that you're not slipping carefully.
Yeah.
Is your best way to cover that scenario?
Theoretically, we would have some sort of brace inside of the medical department. It is a very large device when it's like if it be actually built. So there would be enough room for like a stabilizer. And if the team needed to, like if it say if it was really rocky, like they could remove the bed and stabilize it themselves, like physically carry people out if needed. The wheels would also allow for semi smooth rescue. And so they would still be able to be stabilized if they broke their spine. Yes. Yes. Like if the best buddy got stuck, the bed does come completely out. Yes.
I'm really gonna ask the second question, but you said the fresh air base was boss. How would you plan to do that in cases of maybe blackouts, and especially in this mine? Connection to be able to associate that complexity, like in economy board, they only have a single wire for the radio.
Yeah, that is going to be one of our major challenges that we're going to face with this. If we were going to try to it wouldn't be able to go too far deep into a cave. Like it would only be able to go like probably 500 feet if that would be applicable. But we would try to keep it having battery power, try to face issues with like reliability and battery. with like connection issues, we were going to try to apply like strong antennas to it and try to have a stronger connection. And while it's going into the mine, it would be connected to the surface for about 200 feet to preserve its battery life and to preserve that connection that it needs with the fresh air base. So it's still a challenge that we have to figure out, but it'd be a major one, but it's a really good question.
Yeah, I think that was like all time up for our questions, so.
I'm gonna have y'all close this door.
Good morning, everyone. We hope you guys are all doing well. It is so lovely to see you all here. My name is Radhan Patil.
My name's Said Rodriguez.
My name's Colby McGinn.
I'm Sandon. I'm Shirley Vo.
And we are Team Pink here at Summit. Over the past week here at the summer program, we have built a product that we believe will save many lives in the mine rescue missions. So let's get started. In 2010, at the Upper Big Branch mine, 29 miners were killed in 3 minutes. The cause? Undetected methane buildup. And we see similar gases in our Edgar mine here at Colorado. Carbon monoxide, methane gas, and hydrogen sulfide, which pose risk to our people.
So the current process for the rescue team starts off with the captain who leads the path. He's the leader. He's kind of telling the team how to navigate, where to go. Then that's the gas person who manually scans gas in the ceiling, mid, and the floor area. Then those gases are reported to the fresh air base. Then the map person is a very detailed job. They have to document the location, the terrain, any hazards that they're going through. So that's a very important job. And then lastly, all that information from the captain, the gas person, and the map person goes to the fresh air base, which gets a complex idea of what is happening at the mine. But today we really want to emphasize and focus our attention to the gas person and how we can efficiently improve how we can detect gas in the mine.
So after doing some research, we found out that the current problem with the current process that we see is that when mine rescue teams go in to carry out their mission, they have no prior knowledge as to what the gas concentrations of these harmful gases are in the mines itself.
So that brings us to the question we're trying to answer today. This being, how might we improve the quality and efficiency of gas detectors in mines so that we can effectively alert rescuers of toxic and unsafe locations within it?
And then our solution is gas concentration detectors placed strategically within a mine, as well as a software end that allows us within the mines to easily read that data.
So how our solution works is that we will have evenly distributed sensors at target locations in the cave. So they will detect toxic gas concentrations at each different location to relay to the fresh air base. And so in order to prevent these sensors to keep on working and to prevent catalyst poisoning, then the cave dust, which has carbonates and silicates with them, will react with these sensors and render them useless. To prevent this, we have activated charcoal, and we developed a wire mesh filter in order to prevent the cave dust from ever reaching the pellicers in the sensors, and therefore being able to keep on running so the fresh air base can keep on getting toxic gas concentration data. So basically, the activated charcoal wire mesh filter will filter out any cave dust.
All right, so just talking about the build process itself individually, I worked on brainstorming with the team, as well as researching the problem that we see with the current process, as well as building the slideshow that you see in front of you.
I worked on the software end of it, which I'm going to show you in just a minute.
I was in charge of I was kind of the builder guy. They told me what to do and I just started building it. And I was also in charge of the sensors and kind of what the process of how we're gonna get electricity in the pipes and all that to our gas sensors in the cave.
And my role in all of this was essentially making the CAD model and 3D printing it, and also providing base code for our Arduino and providing support for the wiring system.
My role in this was researching catalyst poisoning and activated charcoal, as well as wiring the Arduino sensor that we will be performing a demonstration on shortly.
All right, so let's look at a demo of the product. So
All right, so this is our lovely model. So this this mesh acts as a representation of the charcoal filter we have over top of the casing of the top of our filters and gas detectors, as well as the wiring. Now, when we take off that mesh, you see the wiring that connects our gas detectors and sensors to the main system. We will talk more about later. Now, onto the main part. Now, this is the casing of our gas detectors and sensors. So when we open it, we have the sensors inside and the detectors. It's very easy to swap it out for another thing and put it in. So you can swap it out depending on the type of gas that's in the cave, much like he said about the different types of gases that are within different types of caves that a danger analysis shows.
So you may have noticed that I was blowing hot air into this Arduino sensor. So this Arduino sensor is a temperature sensor that reacts to hot air. And this will replicate what a chemical reaction that is exothermic will look like in a sensor. And this will actively alert the fresh air base, which is what this red LED light is for.
All right, you're seeing right now is the stock part of it, which I made. Each button you see is a sensor module. Each module is split into 3 different sensors of 3 different types. Here you can see the different values of some of the gas we want to detect. So, yeah.
now just talking about some potential improvements that we noticed, as well as ways we've grown as a team. We believe that if we had more time, we could fit in better sensors. This includes examples such as NDIR sensors, which will allow us to have a better accuracy as to detect the gas concentrations.
For the software end, we're hoping to make a mobile app so that the people going into the cave can easily do it.
And then the ways that we've grown as a team, we first want to thank everyone at Summit, the mentors, all the other students for all the information and all the help that you guys provided for us. So we want to thank you guys. But as a team, I think from the moment we were together in our group, I think we just kind of clicked. We all brought different strengths. We definitely learned a lot of different things about like coding and designing and all of that. And I love how our product turned out. So that's ways that we've grown. And I think I'm super happy with how our product looks. And I think we did great as a team. And I would not have chosen any other team except for ours. So thanks, Abby.
Here's our sources, and thank you, ladies and gentlemen, for listening. We open the floor to questions.
So first of all, great presentation. I really enjoyed. I know you guys mentioned in potential components a mobile app. And so when we visited the Egro line, I know there's Wi-Fi was cut off. So how would that work in a situation?
Yeah. That's a good problem. That's what we thought about. When they're in the mine, there is a good chance, especially if they go deep into the mine, that they are going to lose access to it. So that's why it will save the data. So once they go in, they'll get the latest known time. So hopefully they're not in there for longer than a couple hours. So they will have pretty recent data. Also, there will be someone hopefully outside who can get the data, and then they can relay it to them some other way if there were to be a sudden surge in some evidence.
So you guys program and like the 3D designing of your box to like play all the sensor stuff?
Yeah, so initially we were going to go with spherical shape, but we eventually realized that by having a spherical shape, we would have to severely modify the actual gas detectors and sensors to allow them to fit within the actual casing. So we opted to go for, while a synonymous design with what we originally planned, we flattened out the edges and made it more of a box shape so that we could fit the different sensors inside of it and allow for the room to be there to easily swap it out. Why did you guys choose to use more catalytic sensors rather than NDIR? So that's a great question. So NDIR is very expensive, first of all, and also because it detects different wavelengths between atoms within a particle. So for instance, you have carbon monoxide, which an NDIR can detect. Carbon will have a different wavelength than oxygen. However, for a catalytic sensor can also detect diatomic molecules such as H2 gas, N2 gas, or O2 gas, which an NDIR can't because it is the same molecule.
If you guys had more time to work on your project, how many weeks would you do?
I think we were kind of thinking about it earlier when we were doing the as we were working on it yesterday. We're like, man, I think we have such a great idea, but we just don't have all the equipment and all the, things that we would need. I also think as much as we tried our best, I think we're still missing a lot of information that we could still learn. We're still missing statistics from the Edgar mine that we would also like to have. But I think maybe a couple more weeks and it'll be a lot better. And with more equipment, I think it would also look a little better and work more efficiently also. So I think it would definitely depend on how what equipment we have and, kind of like learning and just a lot of components come together because we kind of just came freshly into it, but not a lot of information and data. So I think that'll take a while as well. So a couple weeks, maybe a month or 2 months.
Okay, that was time for our questions. Good job.
I'm gonna get a picture of it. Thank you, guys.
Good morning, everyone. Start product Mind Mobile.
My name is Vachi Kalra. I'm from California. My name is Erica Suri. I'm from Parker, Colorado.
My name is William Sheddick. I'm from Thornton, Colorado.
My name's Martha Jane. I'm from Fort Worth, Texas.
My name is Parsbach Kerwala, and I'm from Gilbert, Arizona.
So before we actually start talking about our product and our prototype, let me give you guys a little bit of a background about what exactly are mine rescue teams. So mine rescue teams are trained to go underground in different conditions like fires, evacuations, and different things like explosions to locate survivors and to assess the conditions so they can come back and report to the fresh air base. However, this environment creates a lot of different issues like no GPS access, limited visibility, and most of all, limited communication. There's a lot of different roles that people have in mine rescue missions, but our project is mainly going to be helping communication between 4 people. And this includes the captain, the co-captain, the map person, and the fresh air base.
Through our background research, we were able to create our problem statement asking how might we maintain continuous communication between underground rescue teams and the fresh air base while minimizing interruptions to rescue operations and reducing the risk of communication gaps.
Here are some of our early ideas. So at first, we wanted to use LED signals that detect when oxygen levels are low. However, after speaking to an actual miner, we realized that whenever there are excess concentrations of hazardous gas, they usually just bring in fresh air to clear that out. So we were trying to design a solution for a problem that didn't really exist. We decided to we tried to see if we could keep the LED idea and use signals that reroute the rescue teams away from hazards. But because of the high upfront costs and because these LEDs were vulnerable to the conditions inside the mine, we scrapped that idea as well. One of our more recent ideas were RFID tags, which stand for radio frequency identification tags. And we realized these are implemented in a lot of mines, but they're vulnerable to signal interference. That's when we decided to really narrow our scope and focus on designing a prototype that directly addresses that signal interference.
Through decision matrix, we determined the Morse code transmitter was also inefficient and also subject to signal interference. Because we faced problems with signal interference within the RFID tags and the Morse code transmitter, we decided to focus and hone in on that problem. Through further brainstorm and sketching, we created our prototype.
So based on all of these issues and our decision to focus more on communication, we came up with a solution, which is an adaptive communication relay system. What the system does is that it automatically strengthens communication between rescue teams as they go into dead zones, which are zones that actually radio communication just cannot reach, or as they go deeper into the mines, as mentioned by other groups. So how exactly it works is that it's a small portable device that miners carry throughout the mines, and they deploy this in the teams, and they usually carry multiple of these. So what it does is that it monitors radio strain continuously and provides feedback through a color-coded system. So in areas in mines, we're supposed that so what the pack actually shows is that in specific areas, there's either no signal, there's a weak signal, or there's strong signal. So in areas where there is no signal, they would put this pack in that area. And what it would do is that the pack would receive the signal, it would strengthen it and retransmit it. So overall, what's happening is that in a no signal area, now there would be weak signal or strong signal by stretching the radio waves and also increasing the wavelength. And as additional packs are added throughout the mines, it creates a chain of communication.
Let's break down how to use the mine mobile. Use our product to place the mine mobile at intersections in dead zones. Then it would send radio signals across the mine, so every dead zone was covered with radio signal. To know what your strength is, you would have a green light. To represent strong signal. A yellow light to represent weak signal, and then a red light to represent no signal.
The device would then rebroadcast the radio waves to the rescue team with the antenna. The device is also portable as it would hook onto a carabiner similar to the miner's belt, and so that they can carry it around. It is powered by a USB-C charger and a rechargeable battery, so it can be reused over time.
So based on all of this on our prototypes, what exactly is the impact? So as reiterated before, obviously there's the communication factor that we talked about. So now with the radio signaling reaching further into the mine, you're able to communicate with the fresh air base and underground. But overall, just having this pack, it increases situational awareness, increases responder safety, and overall miner safety. And we looked at the cost of the pack, comparatively looking at the lights and the sensors and the different things that are inside of it. Costs about $35 to $40.
So we do have some future improvements that we want to add. So right now our pack is pretty portable, but especially for mine rescues, it's kind of hard to carry multiple of these, and that's just extra weight added that you don't need. So what we wanted to do was develop an autonomous deployment relay vehicle. So what it would do is it would carry just a bunch of these packs, and wherever it detects dead zones or where signals are low, it would just drop one of these packs here using a motion sensor, and it would extend the signal. It would follow the miners as they go on their expedition or whatever they do and the rescue, and it would help them by making it easier for them. So some of the things that our robot would use would be LiDAR sensors, depth cameras, and an LED lighting system to make its way through the mine and follow the miners as they make their way through. As you can see, our tag of the robot, the box at the top is where we would fit a bunch of these mine mobiles. The antenna would detect the signals from the radio waves, and then the motion sensor at the bottom would help the robot navigate its way through the mine.
Let's reflect on our experience. We've used an engineering mindset to develop and solve problems. We've used a decision matrix to select the most effective design. Then we combine all of our ideas to create a strong final product. We improved our teamwork skills, collaboration skills through supporting one another, splitting the work, and discussing our independent ideas with each other. We all stepped outside our comfort zones and gained valuable experience in different fields of engineering. We learned so much from our different professors, workshops, and mentors.
These were some of the sources we used in the creation of our presentation. We wanted to thank our mentors, our professors, and especially Mr. Bruce for all their expertise in mining and the industry. That helped us a lot. Thank you all for listening.
Questions? how do we conquer rocky terrain? What happens if the robot were to flip over?
We would have a miner either go up and pick the people back and fix the robot, or we could design better wheels so that we can account for the rocky terrain.
So we actually looked at, like, there's a lot of robots that are actually being used currently, like, we looked at research papers. So we kind of tried to mimic like similar wheels that they use that are made for different rocky terrains. Obviously, there are some limitations to like turning over, as you mentioned. So that is something that we need to work on.
Yes.
It wouldn't be too large. I would say probably about this big. It would just want to fit as many of these as possible. So about the size of a little mine cart. Yes.
I really mention about also projections. Does this price to be put on the market or much richer? It's the market price.
Market price would probably be around like $50 to $60 per bottle. Any other questions? Thank you all. Thank you.
Take a picture.
Thank you. Great, great.
Hello everyone. Welcome to our summer presentation. This is our mine rescue system. And this is our team. I'm Ronak. I'm Lucas. I'm Dante.
For this final project, we were asked to come up with something that would help both the communication and navigation of the rescue team. During our research, we found multiple problems such as flooding, explosions, fires, and dead zones, which results in the loss of communication between the teams and the miners. In consideration of all of this, we came up with one simple question, which was how can we improve rescuers' ability to locate miners efficiently and quickly in emergency and communication deadlines. Why does this matter? It matters because it is vital to locate someone quickly and efficiently, due to like lack of oxygen and other things that could quickly significantly involved. Due to facts as the miners, families, companies that are building the mine, and the rescue team. Some of the limitations and considerations that we took into account were the harsh environment. So in the event that the ceiling or the mine walls collapse, that causes a lot of smoke and debris. So visibility can be very limited. We also took into account dead zones, which are when signals like GPS, Wi-Fi cannot get relayed from the miners to the fresh air base or vice versa. And the last thing that we took into consideration was the limited space within the mines. So in order to address the issues that we mentioned previously in which miners are trapped, we developed these safety lights. And these would be small LED lights that would light a path to the nearest exits in a mine, and they're activated in the case of an emergency. So to detect these emergencies, we will utilize radio frequency identification, which is also known as RFID, and this will detect where the miners are. And the way that this works is that there are tracking checkpoints every 15 to 20 meters, and they detect the individualized RFID tracking chips in every miner's path.
Secondly, with the autonomous robot, it has a LiDAR camera, which while may not be able to go through, accurately map some of the mine conditions. And if LiDAR is not working, there's a thermal camera, which can detect people in the case of smoky conditions. there's a gas sensor that can detect dangerous levels of gases. And then we're also working on our ultrasonic sensor, which can track the RFID chips that smart house.
Alright, so now I'll be talking a little bit about like one of the models that we created. So we created an AI model in order for mine inspection because it is very dangerous for humans to go out and scout mines because of the potential for rocks to fall or mines to fall down and cause a lot of damage. So one thing that is important to note is that the robot's camera captures 6 layers of information at once. And what we did was we generated 2,000 synthetic images that simulate the real like mine conditions as such. And this model is a type of neural network called a UNet. And it looks at the 6 image layers. It compresses what it sees down and then it expands it. And afterwards it colors which cracks are like good or bad. And it was trained on 1,500 images and it's on 3,000 images that I'd never seen before. And so ultimately, you can see that the model finds 98.9% of real facts and almost never misses one. And this is the most important number of this model. So now we'll be doing with a live demo. So this.
So our LiDAR system is designed to detect, like said earlier, RFID chips in hard hats, and use that to locate miners in mines. These systems placed every 10 to 20 meters will allow the fresh airbase to look at the computer and see, say, miner A passed the first sensor, but not the second, allowing us to understand that they're within the radius of these two sensors. I showed a diagram later. This is an example of that system, as if there were 2 LiDAR sensors on the right, left. These are not LiDAR sensors, but they offer a representation.
Yeah, and then so then like for example, like if the person's walking here, then it detects and then it flashes the first light, and then if they continue, then it flashes both lights, which show the person moving forward.
And along with common stuff. So this is an overview of what I just stated. These LiDAR sensors, as shown in this mock-up system, would allow us to track when there's gas sensors to chips in their helmet. They would also include safety lights, which are in the event of an emergency, can be turned on by the fresh airbase. This would allow the systems to line up in the direction of any trapped miners. Say, a mile down the mine shaft, there is a miner. There are turns and twists that a rescue might not be able to navigate confidently. But these lights would allow them to just follow the next light until they find the trapped miner. We can go to the next slide. This is an example of what this model would look like. The green lines shown are RFID trackers. We would be able to know what sector miners are in based off these trackers. If someone passed the first sensor on sector 1A, we'd be able to know that they're in sector 1A because they haven't passed any of those 2 stats of leading to 1B and 1B. And so this will allow us to assume where the miner is in a certain area of the mine shaft, leading to quicker rescue. This is a diagram of what we use. In the top left is the RFID scanners CAD. We did not utilize this in our project. And in reality, it's around 1.5 feet in size. We didn't use it due to limitations of time and cost. These systems cost around $220. Below it is this CAD model here. This was our mock-up for the small representation of what would look like a mine. These would be hardwired, and so there would be no need for signals. In the case of collapse causing a severed wire, we would still they would use the most recent upload data.
And then so the second part of our design is the autonomous robot. So our first iteration of this is what I have here. It has a LiDAR camera, so it can accurately map the mine conditions. And then in the event that there is smoke, so the LiDAR camera would work, and then we would pivot to the thermal camera, which can effectively determine body heat and locate trap miners. And then it will also have a gas sensor to detect levels of dangerous gases. And yeah.
This is our secondary prototype. This is 3D printed. It has a hinge right here to open, so you can easily reach all the components inside of it. It will work very similar to it. However, because we do not have a LiDAR sensor or a thermal camera, it is very rudimentary right now, as it's just the outline of the box. You did in fact have a third model, which was much better than this one, which would have worked, but the printer failed 3 times, so you did not have it.
We're also working to incorporate the RFID onto the robot so that it can also be tracked by the scanners.
Okay, so I'll be giving a live demo of a simulation that created where to throw with the powder.
While he's handling that, I'll discuss the benefits of using RFID sensor rather than solely motion track. In a system like a mine, the RFID sensor will be able to distinguish between different tags of different miners. This would mean that even if there are 5 miners in a mine walking, and multiple pass the motion detectors, we would be able to distinguish every individual miner, which would lead to less system complications. Also, mounted on the bot, it allows us to detect miners, helmet signals in stuff like smoke and in rubble, leading to an even better system at locating miners than an RFID camera. To where it can just detect the existence of someone rather than having to look for them physically.
Yes. Yeah, we can go to questions. So,
What would you do if the joints were just sensors like the wireless sensors?
yeah, so in the event that the wire snaps and we lose like connection, it will take the last known data and send it to this.
Also, it's supposed to be
Right.
This is the simulation that was created. So here you can see that there are multiple options because of the conditions. So like in case of like the real mine, there are multiple miners. So just say after they do that. So in real mines, occasionally there can be smoke. So like showing the smoke clearing and also clearing it, which there isn't. And additionally, you can see on the right that there's the LiDAR, the thermal, the gas, I know it's working up before. And then you can see someone click on gas leak. At some point, when the gas sees like the acceptable concentration, then they'll see like all these LEDs flashing, showing that the miner will get out of there as soon as possible. And ventilation, which reduces the gas levels until the LEDs get to normal. Then there's also some specific areas such as like where the existing collapse, for example, that was simulated, and like flooding conditions also, which causes the miners to split this as much as possible. And then 2 other things are evacuate and deploy rescue. So it's like actually simulates rescue people coming to miners. And yeah, that's pretty much the simulation.
So essentially, in final analysis, our big question was right about there. And we addressed the harsh environments by creating an autonomous robot that is able to successfully navigate uneven terrain. And we also included the LiDAR as well as the thermal sensor that can detect people. Then we address the signal blocking with guided LED lights that can help trap miners.
Time for the one question.
I open-minded was sorry, I base emergency. That's really at that point, there aren't many options. I have seen uses of industrial RFID tags being infused into vests, stuff like that. But in mine's case like this, the number one priority is to keep your hard hat on. And I think in that rare occasion, which it really does not happen that often, there's not really much we can do about it. Other than the RFID tag thing. It would just be up to the regular standards of rescue workers that are to locate mine finders.
Welcome back now. We are seeing someone at the top 7 and soon we will be talking a lot about my model of this. Let's see first.
Hello, my name is Brady McGinley. I go to Dorley High School. My hometown is in Florence, South Carolina. Some fun facts about me is my favorite color is purple. I enjoy reading, hiking, and exercising. And I've been an athlete for 3 years, 10 to before.
Hey y'all, I'm in charge of the graduate philosophy system school. I live in 4 states of Florida. I love to read, I love to hive, I love chemistry, and I volunteer at my local and physical library. Guys, like visit Toria Seminole Laguna. I go running a research college high school in Colorado. My favorite is food theories and I live the outdoors of software. And I volunteer with the nonprofit.
Hi guys, my name is Arden Swaminathan. I'm from Cherry Creek High School in Greenville, Colorado. Fun facts about me are I love to play soccer and I also volunteer at Project Q.
My name is Leo Zhu. I go to Towson High School. I'm from Fruita, Colorado, and I volunteer at my local dinosaur museum. And I think that audiobooks are overrated.
Okay. Our project aims to help three main problems found in mine rescue operations. The main one being human errors, which are the main source of casualties and injuries in mine operations. And that is doubly true for mine rescue teams, as the adrenaline and stress of the situation is more likely to make mistakes more often. Missed communication, as when they are going through the mines, they wear dust masks and other such protections to prevent them from inhaling things and substances, which can make miscommunication more easy, will happen more often and such. And of course, time constraints, as they are rushing to save multiple people that could be trapped or injured in the mines.
The accuracy and efficiency of mapping technologies used during mine rescues. And we hope that to do that by reducing avoiding human errors and the technologies.
So the project we started out with was like, at first we did have a mapping idea in place. Like we went with our first idea and then stuck to that to the end. We first thought of like an armband that we could use, preferably something that we can use our arm to like scan. And we did go with that idea where we have a sort of tablet that this sensor, which can be placed on the top pad right here, relays the information to. The video in the middle is the start of the sensor built into this device right here. And the last picture you see is the Arduino kit we use.
So our solution was a Arduino mapping device that in the future aims to be installed on the helmet and is transmitted to a tablet worn on the forearm. And this is because in low visibility conditions such as smoke or darkness, miners require instant knowledge about their surrounding environment. Furthermore, current mapping technologies are more analog and digital, which makes them more prone to errors. Consequently, digital data allows faster and clear communication between the mine rescue team and the fresh air base. Okay, as we look towards the device in hand right here, we can see that there's going to be three main components to this. The first may be the Arduino Uno kit we use, which is going to be inside. This is going to relay all the information found by our sensors to directly to the computer we're going to be using to connect this and show you a live demonstration later. One of the sensors is using is a time of flight sensor, which uses ultrasonic waves to get the distance between objects in through a certain radius. So that's going to be right here. We also have a 9-axis gyro sensor that we use to properly map all 9 axes and the entire mine rather than just facing one direction. So we're going to be showing you a live demonstration about how HTML files 3D map. Okay. As you can see, like at first glance, you can see that like that little tiny sensor is tracking my distance from my hands. So the further I move away, the further the sensor is going to move. But the closer I get, the closer it's going to go to. And when I record every reading for every second, here, I can move the sensor around, which should be able to map everything within a certain distance of our so right now I'm just pointing it randomly as a reader, and it should make a terrain map like you can see. So at this point, like this sensor isn't really going to be the most popular thing you ever see. This sensor really depends on how you're going to implement this into a mine. Because in a mine, you're going to have there's going to be a much larger area. You're going to have to require a much larger sensor, a much larger device. But with our limitations right now, this 3D mapping technique shows like what are the possibilities of what we can do in the future if we did have more time to make this a much better product.
Now, there's always area for room for improvement. So what we want and that first we have included a data storage system, which would allow us to keep our map plans, improves our software, and then this would serve as models for future rescuers to use, and also help them enhance our sensor capabilities by elongating the distance or improving a wireless function, stabilizing the input to the output. And these are some components. Just here,
So about your sensor, how both one and two, if you said it'll be like in front of the hard hat, but that's usually the place where the light goes for the miners.
Well, obviously, there are some limitations to this, but this is in the project box. That sensor can be modified and adjusted to like fit with the light. So obviously, like the light is going to be there, and that's like an important area. But like there are possibilities where we can like fit the sensor around and like mold it to the hard hat itself. Which would require much more resources and much more time. So,
And would the added weight cause like instability issues with the miners themselves?
I would say this is pretty light so far. The like more technology would just mean like more advanced technology wouldn't necessarily mean more weight, right? So there are problems to that, but right now, I think it is still okay.
Yes.
So we didn't really research into the unit price because we just accessed whatever we could through our workshops and everything. So this sensor was actually from one of our workshop teachers, Professor Cusco. He was kind enough to lend us this sensor, and we really didn't have time to research the price and effectiveness of this because like this is still a very like a really like early prototype. That's all. Yeah, thank you.
Yes.
Okay, we can go. No, what? Can you put wireless? So this is still wired. Wireless would need something to connect with the Arduino itself. We really didn't have access to that, and I don't think we really did any research into that. These are just areas in Berkeley where we can possibly make this much more efficient because a wired wouldn't really work with a hat. It has to be wireless. But right now there's nothing more we can do. It's just what we had to work with. Yeah.
In the use application, this would be used by the map maker, or would we honestly eradicate the rule of mapping altogether? There still be something like that, or would the rule map we are since he's taking points, and the map man just his job is to be the fresh air base.
Okay, so the map person is obviously gonna have a tablet, right? So he's gonna relay the information directly to his teammates and also the fresh air base, right?
Yeah.
So this sensor doesn't necessarily have to be only for the map person. It could be for all the roles we have because it's gonna go onto their hard hats, right? So more data just means more accuracy, right? The more data you have, the more accurate the mine or the terrain map is gonna be. But the main function is gonna rely on the map person communicating what that means.
To comment to what I said, ideally the top person would have to do this on their far shot, but it's very if all members of the rescue team have the tablet so that they receive the updates as well as the any more questions? Problems? Yeah, thank you for your time.
Hi, we are Team Orange, and my name is Inho Lee. I am from Colorado Springs. I'm Ellie Goldberg, and I'm from Denver, Colorado.
I'm Megan Ong, and I'm from Houston, Texas. I'm Emily Garnell, and I'm from Livingston, Colorado. And I'm Soleil Bacorio, and I'm from Denver, Colorado.
And our problem statement that we tried to address through the proximity tag was how might the mine rescue team more efficiently and effectively locate trapped miners in order to save time, increase safety, and lower risk. The team came up with this question through extensive research that found several problems in locating for mine rescue operations. This included the average rescue time for long trapped miner incidents being 14.9 days, the global fatality rate of the trapped miners in unknown locations being 73.4%, many mine rescue operations beginning with uncertain or incomplete information, and the majority of fatalities happening in the first 5 to 10 days after entrapment. This makes rapid location and rescue critical in the mine rescue operation. A specific example where a mine rescue operation had difficulties locating was in 2006 Beaconsfield mine collapse, where essentially a rockfall trapped 3 miners, killing one and leaving the other 2 trapped. but it took the mine rescue team 14 days to successfully rescue trapped miners, 5 days to pinpoint the trapped miners' locations. So when trying to develop a product, our team focused on reducing the time it took to pinpoint the locations of trapped miners. But this actually wasn't our first question or problem we tried to address.
The first initial approach to this problem was to protect miners' safety from toxic acid by repellent in some shape or form. And our initial solution to this was to create a foldable structure containing that could store like O2 tanks within those structures. And we also added additional features such as an inflatable tent that could pump O2 for the victims and a heated blanket for the victims' warmth. However, this initial solution did not follow through due to time constraints and the complexity of this whole solution. So in response to this, we decided to change our approach completely.
Our solution is an infrared raised proximity sensor. The device buzzes and lights up when triggered, like this, alerting rescuers of a miner's presence nearby. Miners would have a transmitter, which is represented by the remote here, and rescuers would have a receiver, which is our Arduino device. Although this functions, the final product would be off, meaning an unconscious or impaired miner would still be found. We would use radios instead of and over longer distances. So the device would emit sound from the miner's side to alert rescuers and flash differently based on proximity to give the rescuers a better idea of where the miners are located. Both parties would be alerted of the other's presence so that the miner could call for help and make the whole process more efficient.
The materials we used for this prototype was an Arduino kit and board, an LED light, a buzzer, a remote, and pad, which are 3D printing materials.
The final code that we used to make this whole device work was using an IR remote and coding it to the IR sensor on the device. And the down arrow on the remote makes both the buzzer and the light go off, and then the up arrow just makes the LED flash. And the IR remote represents what a proximity sensor would do in the final device.
There are still constraints to the functionality of this test. Signals may not transmit through long distances or large amounts of rocks. This means that rescuers still need to have a general idea of where the miners are, and those in odd positions may not be rescued as efficient. For a large mine, the cost would be quite significant, though if it could save lives, this would definitely be worth it. And there would also be additional weight, which might make miners wary of using it as they are already carrying lots of.
Our first challenge was that our first solution of the foldable structure with the oxygen tanks wasn't feasible and wasn't actually needed to aid the mine rescue. Our second challenge was that we struggled to find a solution for our. So most of our solutions were either already created or weren't actually able to be realistically created within the time frame. And our third challenge was that we wanted to add a louder speaker on the proximity tag to better alert the rescue team, but the materials given only included this small buzzer, so we used that and an LED light instead. Through this project, we gained communication skills by working together on the prototype. We learned more about how mine rescues work and problems in communication and navigation through the mine tours. We learned skills in coding Arduino, soldering, 3D printing, and modeling. And we learned to persevere through obstacles that we faced. In conclusion, our small proximity tag is not meant to be an all-encompassing solution. It is simply meant to help aid mine rescuers in finding trapped miners faster. It's designed to save hours or even days when in the early stages of mine rescue, when they're just trying to locate the people so they can figure out how to safely extract them. This will allow them to get medical attention quicker and help save lives. These are our sources. How small is the proximity tag?
Well, I think it would be as small as an air tag that we could just attach it on a random piece of equipment, or you could wrap it around our waist. Well, what do you mean when you say your original solution was too complex?
It was just it wasn't really necessary, and we wanted to have a working prototype, and it wasn't something that we could forward.
How many you guys find the way to the top of the
It would be fully encased in our actuary. Arvin?
Okay, so if you did have like time and more money and more resources, what would you replace the IRS with?
Something like a radio, sensor so that we could go over longer distances.
Could potentially be additional weight to the miners. How heavy do you think that would be? Because once we're able to put that into the plastic liners, like what do you know?
This is only just a prototype, like we said. This is gonna be like probably as small as an air tag, and it probably wouldn't even weigh less than, I wanna say, 50 pounds, just like a phone. Like, yeah.
Then you expect a little bit to is the model.
We might not be able to hear it, but that's why we added the buzzer too, so it would also vibrate to let you know. And if in a emergency, mine rescuers would be like constantly checking it to make sure that a person, like nobody else would be able to, or they would be able to find.
To put it on the minor operating custody or with the sayings, like signals or when the minor has to go down to leave. That leads to issues with it. If they pass out and they kill and stuff like that.
It would all be automatic so that they wouldn't have to do it.
If it's automatic, then how long do you think the battery life will be? How often do you have to charge it?
That's a great question, and we would have to do more research, but it could definitely be something that you charge it every night and then take it into the mine whatever.
Good morning, or I guess by now, good evening, everyone. We are Team Violet, and we present to you the Ready to Go card. To introduce the team, my name is Berenice McGee Sinclair. I'm from St. Paul, Minnesota, and I attend Central High School.
My name is Zara Siddiqui. I'm from Katy, Texas, and I attend the Audi International School.
My name is Andres Rodriguez. I'm from Laredo, Texas, and I'm attending United High School.
My name is Ryan Nugent, and I'm from Scottsdale, Arizona, and I attend Desert Mountain High School.
And I'm Dia Methla, and I'm from Beaumont, Colorado, and I attend Madison High School. Now to talk about our research.
Okay, so before we can actually choose a problem to fix, we have to research different components of mine rescue. So for a brief overview, the basic rules are the captain who sort of leads the operation and makes sure that the space is safe to go into. The gas person who checks for toxic gases and makes sure that everyone is safe to enter. And the map person who sort of maps out the area, maps any toxic risks or anything like that. And then the medic who, in case of any injuries or anything, would assist in injuries. So to do this, we first got access to a Colorado mine where we went and saw firsthand the tunnels and things like that. And we also talked to a mine rescue expert who gave us insight into the research process. So while we were researching, we came across a story that caused us to focus on improving the medical part. So basically there were in September 2023, a miner named Mark Dickey suffered severe gastrointestinal bleeding in a mine in Turkey. And to get the rescue part through, they actually had to blow up some of the mine because the rescue part was so big and bulky. And it took over a week to navigate the cart to the surface.
To start, you might be wondering, what does the medic do? Well, in the rescue team, the medic helps treat and assist patients that are underground in order to ensure a safe evacuation. The medic is also in charge of maintaining the medic cart down below. Some obstacles that they may face though are that the medic cart can become increasingly heavy, which can cause severe fatigue in the medics. The headlamp also has limited visibility as the headlamps are designed mainly to light up what's right in front of them. And so their peripherals tend to be a very big blind side and it can lead them to examining not as efficiently as they could. Their supplies also aren't always secured onto the cart, which leads us to our problem statement.
How might we optimize the medical cart to best handle emergencies if works?
Well, we had a lot of ideas about how to fix this. Early designs involved just completely reworking the medical cart and completely changing the designs, the wheels, the way it worked, the way it was like built. But we talked with Bruce, a professional in the field, and he told us that our designs were just way too complicated. We were overcomplicating a design that was already working in the mines. And so instead, we try to think of what the stakeholders, the miners working in the mines, would actually want and would benefit them. And so we thought of something that would be practical and easy and would hopefully not cost a lot while also being compact enough that they wouldn't have to face any issues within the mines.
Some of the ideas that we thought of were lighting, carbon fiber, adding suspension. In a lot of mines, there's big rocks, little rocks, and they are narrow. So we thought of a suspension system to better traverse the mine. We also thought of carbon fiber, which unlike plastic will not degrade and it's much stronger and lighter than plastic in the manufactured state. Having padding on the cart will mean when the cart hits the narrow walls of the mine, the impact of hitting the wall will transport to the padding and the patient.
So using a pre-made, using a Grow website, we use a pre-made CAD model of the litter box. And because it had a complicated design, we only cut down what we actually needed. So to create that model, we used tools found in the classroom and hardware. And moreover, to create the LED lights that will be found on our actual products, we use an Arduino Uno R3.
And so this is our final design. You can see here, this is the 3D printed part, which is like the base trifold of it. This is the base trifold of it. And in our final product, it would have holes in it and it'd be made out of carbon fiber so that it's lighter and easier to carry, but it'd still be able to support the patient. These are the straps to hold the patient down. This is the basket to keep all the medical supplies in. And these are the LED lights to improve visibility in the mines when treating the patient. But on the actual product, it would be more like LED strips because you won't have to manage all of the wiring and stuff like that.
So for the LED design, we first used a series circuit for the LEDs, but we later realized that would actually be really inefficient and would cause problems. The reason being is that if one LED light goes off, then all subsequent LED lights would also go off. This creates a problem. So we rewrote the whole thing and we employed a parallel circuit. This ensures that even if one were to go off, the majority of the lights still stay on. And right here, we have a switch that we can toggle between on and off.
And special thanks to Malachi
for soldering the switch for us. And so now we'll just plug it in. Okay. Okay, it seems to not be turning on. That is just a bit of a malfunction, but it will be turning on. It would be turning on all these lights, and it would create a type of a light cast, so that the medics can use.
You can see it in the picture.
Yes.
So throughout this project, we faced many different challenges. The first one was during the brainstorming process. Like Ruby said earlier, we were overcomplicating all of our design ideas and all of our solutions, trying to solve problems that didn't exist. And after speaking with Bruce, we decided on a simple and realistic solution.
Another challenge was troubleshooting with the 3D printing. This 3D printed part failed the first 2 times we tried to print it. And then the third time we added a rim around it that was part of the support so that it would help it stick to the plate better so that it wouldn't lift up while it was printing, and then that allowed it to print correctly with time after that. And then another problem was attaching all the LEDs to it and trying to make sure that they didn't come unplugged.
We also learned quite a lot with the Arduinos. We learned especially how to manage the current, the power, and the circuiting with the LED lights. And we also learned how to keep stakeholders in mind when designing. We made it as simple as we could. We realized that by using a trifold design and using simple LED lights, we could avoid overcomplicating it or over-engineering it. And this ensures that we make a product that will be profitable.
Yeah, so these are a list of our sources here. We would love to thank all of our mentors and our teachers that we've experienced or that we've talked to throughout the week. Any questions? Yes.
The LED lights, would they be on at all times? Like, how would you do them like going out?
Well, they wouldn't be on at all times because the headlamps that the miners have are for navigation and direction. The LED lights would be more of like a last resort resource so that the medic can put the bed near the patient and examine them in real time with a brighter area of visibility, and then they can assist them in that way.
Got it. Sorry, can I add on to that? Sorry. So right here we do have a switch so that turns it on and off. That makes sure that they can choose when to turn it on. And as she said, it's more of an auxiliary use. So they already have that headlamp, and that headlamp only focuses light on a certain region. So this ensures that if the person's on the medical bed, then they can be treated on there, and a medic can actually treat them.
So, why did you scrap your suspension system? Yeah, so originally we had a lot of ideas. Like we said, we had a suspension, we even had a motor. But when we talked to our mining expert, Bruce, he actually said that a lot of these were problems that would, if we were to fix them, it would actually bring more bulk and more weight than the current design. So we really tried to focus on only choosing things that would add minimum bulk, like the carbon fiber frame and the LED lights, which would actually make it lighter. So yeah. What do you say is about creating that?
The hardest part would most likely be the fact that we had to basically scrap the original design of putting it into the series. When we first realized didn't know what to do, but then we realized after doing a bit of research that we had to use parallel, and that would ensure that the majority of the lights would stay on. And of course, one added benefit of that is that it keeps it organized so that we can better arrange LED lights around them.
And to add on to that, like Andrew said earlier, we switched to a parallel circuit because it allows that if one of the lights were to go out, the rest of the circuit would still be working. And it also helped us manage our power better because with this many LEDs, the current would be shared through all of them and it adds too much resistance that all the LEDs would be a lot different.
Yeah, so first of all, great presentation. I noticed that in the final design, your LED lights are powered by, I think, a 9-volt battery, right? So this was produced up to scale. What would your power source?
I think I would say that most likely some sort of like car battery in a way. Of course, this is obviously not to scale, but that car battery would provide enough voltage and power and current to support the LED lights. And also these are LED lights, so we'll still be implementing the LED lights into the actual final model if we were to make it. And because they're so concise and simple and they don't take up that much power, they don't really need so much energy, just enough to keep it on while they're doing the proceed.
And to add on to that, the reason we chose LED lights is that when we were talking with Bruce, he explained to us that if we chose a lighting system that was way too expensive or overpriced, it just wouldn't sell on the market and it would actually end up not benefiting the miners at all. And so we chose to do something that was very simple and easy so that the unit price wouldn't go up too much.
Yes, I got it. You read. The last one is the
Right. Hello, everyone. My name is Sophia. I'm Katie Clark. I'm Cora Lamberton.
I'm sorry.
I'm just and our project is the biopolymer dust sequencer. So our issue was the particles in the air within the mines. So drilling actually creates a lot of dust, which will go airborne and get into the lungs of miners and scratch them up and create all kinds of problems. And mainly these dusts are coal dust, blasting dust, silica, and asbestos. And then these diseases that it can cause is obviously pneumoconiosis, which is black lung. It's caused by the inhalation and accumulation of coal dust. And, it's possibly fatal. And then silicosis, which is the inhalation of silicone dust. And then asbestosis, which is inhalation of asbestos fibers. COPD, which mimics the effects of smoking and is a chronic condition, and cancer.
With our research, we were left with the question, how might we prevent rather than cure long-term diseases affecting miners stemming from airborne particles? So the current solution is using untreated forms of water, such as groundwater. Unfortunately, that has a surface tension of 72 micrograms per liter, and 10 microns bounces off the surface, and 99% of asbestos fibers are less than 10 microns, and RCS is always 10 microns or less.
Which led us to our solution, the biopolymer dust suppressant. We added certain chemicals to the water to make a solution that more effectively captures the particles from the air.
So we had some challenges and we were able to overcome them. So first, we had trouble finding an empty spray bottle, but we overcame that by looking through every element tool. We had an issue with scraping and polishing the spray bottle. We were able to use a screwdriver to remove those systems. We also had trouble finding the initial materials we had chosen originally, but we were able to use dish soap, lime gel powder, and also sports. And also we had a connection with our cathode wires embedded, so we just debugged every technical problem. And lastly, we had trouble finding the exact measurement, so we created a formula to get those.
All right, so let's do a demo. So here's our spray bottle, which would mount onto a wall, right? And there's a button which activates a autonomous spray by activating this servo to rotate, which would trigger the spray trigger in order to spray. So if I were to click this, it would spray the spray. Okay. All right. And in order to demonstrate how this works, we have 2 bags full of dust.
Someone will use water.
And this one is going to use a solution. But normally our solution is great for really small particles, but we noticed that it works great with dust as well. So first we'll start off with the water. So you'll notice that the water is spraying, but it doesn't really accumulate, and it leaves trails that rest the dust because of the surface tension. It doesn't absorb that dust. And here we have solution. Yes. So as you'll notice, our spray, it picks up the dust really easily with the low surface tension, and because of the liquid inside of it, and if we did this, it'll pick it up and pick it down with it. And since it's biodegradable, it will all disappear again.
All right, so here's our meal code. Up there we got our pin setup, and right below we have the movement and rotation.
You'll notice that there's not room for a sensor in the code, and that's because we didn't have the resources and access to have a sensor that would do the dust particles. If we did, we probably use this SDS-11 sensor. It's a laser sensor. It shoots out light and then reads the amount of light reflected off the dust particles through the air. We did leave a nod to sensor in our circuit by using this button. It essentially breaks up the power that would be running to the servo, so we can still control it and test it when we want to have it, instead of just having the servo always.
All right, here's our CAD design behind our model. So you'll see our big sketch there, and it has very constraints, but by using our road trace and rotating it 360 degrees, we were able to create the model design before adding the wall.
So now let's talk about the impacts from our solution. We have two main impacts. One is human centered, when we're seeing that we're preventing the root cause of diseases like asbestosis and pneumoconiosis, where we're creating a skin over the dust rather than just making it wet. So preventing the dust from escaping the water and going into the air and being breathed in. And it's also biocompatible, which means that it's completely safe for humans to interact with, and the runoff is also safe to interact with. And that brings me to my next impact, which is operational and environmental. So we're seeing that the humectant and the surfactant actually reduce the amount of water that is necessary to make the spray. And we also see that we're accounting for the factor of safety and different buffers and errors that we might have. And everything's biodegradable and it has the same viscosity as water, so it's prevention buildup in the process. So let's talk about the chemical breakdown and how we actually got to the numbers we did. So we used, so the actual ingredients that we were supposed to use was acetic acid, chitosan, alcoholic glucoside, and glycerol, but we didn't have access to these, so instead we used things that were commonly found, such as lime gelatin, which replaced the acetic acid and chitosan, and corn syrup, which replaced the glycerol, and hand soap, which actually contains different types of alcoholic glucosides. Our procedure was to dilute or dissolve the humectant, which was chitosan or gelatin, into an acidic solution, and then add the rest of the ingredients. So let's talk about the chemistry. So the surface tension is actually decreased by the surfactant, which was the alcoholic glucoside, because it has a hydrophobic tail and a hydrophobic head, which wedges itself between the water molecules on the surface, which on the surface of the water, which essentially creates wedges between the attractions and lowers the surface tension from about 72 millinewtons per meter to about 28. And then we also see the ionic charges. So things like chitosan and gelatin are positively charged in acidic solutions. So it attracts the negatively charged dust particles such as silica and asbestos. And we also use the critical miso concentration to prevent the surfactant from clumping together. And we also accounted for the factor of safety, which essentially means that we accounted for the fact that some of the chitosan would have H bonds and dipole interactions with the water itself, which is polar. So we added more than we need to and accounted for flash evaporation, which means that the droplets in our spray are bigger than standard water droplets, so it takes longer for them to evaporate. These are our references. And
Thank you to our mentors, the SUMMET team, and also our donors. Any questions?
How did you decide like the exact concentrations for like each of the materials, like how much percent of everything? Yeah, so that's kind of what I mentioned briefly earlier about the critical miso concentration, which essentially means that it's the threshold at which the surfactant, which is like alcoholic glucoside, starts clumping together instead of acting as individual molecules. And we want it to act as individual molecules, but essentially the concentrations were all public information. So we averaged out the different alcoholic glucosides that were present in the soap that we used, and we got a concentration of about 0.04%, but we used that to determine the rest of the concentration.
Add on to that, find the percentages that were in the solution as like a makeup. Roxy did a bunch of calculations using prior predictions.
Yeah, so this thought and maybe probably everything like that they conserve resources is water and doesn't have the regular environmental impact. To add on to kind of like to get asked, how did you all come up with the formula for the solution?
Yeah, so we knew that we wanted so first we had to analyze what the water currently was doing, and we saw that any sort of particle that was under 10 microns just bounced off the surface of the droplet. So it wasn't being attracted. So we know that there were two problems. One is surface tension. We knew that the attractions between the water were too strong for dust particles, smaller dust particles that penetrate.
So we knew that our spray had to one, decrease surface tension, and two, keep the dust inside the water instead of the dust escaping with a little bit of water attached. So we knew that we had to create some sort of attraction between the water and the dust to really seal the dust into the water.
Create a system to attract water droplets, we slide droplets.
So can you say that?
And the concern with aerosolized water droplets and mist toxin.
Yeah, so we were planning on creating a sort of so there are kind of two answers to that question. First of all, the runoff would be treated by the miners, and they already have a system in place. So we're not like reinventing the wheel necessarily. We're going to keep the system that they already use in place. But additionally, we're seeing that the positive charge and the negative charge create an ionic attraction between the silica or the dust particles and the humectant, which kind of neutralizes the acid or the particle and makes it less lethal.
Now, as for the spray itself, it is completely harmless. It's biodegradable. Nothing other than harm. Most of them all of them won't harm anything. It doesn't have any reactions with any of the dust particles that would cause something that would harm.
It's our price for this is like around $75, and mostly all the materials except for the green tatted part is you can find out your local Walmart or Target.
Yeah, so actually we're kind of inspired by some of the presentations we saw last week. So we saw that one of the presentations actually addressed kind of like the part that happens before the actual rescue or the part that happens after, and we kind of wanted to address the management impact. So we landed on asbestosis and pneumoconiosis, which affects about I think 11,000 miners in the past 20 years. So we knew that we wanted to address the long-term problem, so we were able to go from there and really limitations like the normal water use.
Also, currently they just use straight up water, and we thought that was not only ineffective, but not able to get rid of that asbestos that's in the air, which is still causing problems like black lung and cancer. So we're glad to get rid of it.
We're talking to multiple teachers or professors that we interacted with over this week. This one has like the middle of what we got.
Can you guys give us a price breakdown of that $75? So I would say maybe like 5 to 10 with the actual spray model, because what we did is we made a 3D printed spray model, and then we had to find another one that had like the sprays and also like a little program, and we had to cut that off and put it together. Then maybe we probably don't know the price breakdown for the sensors and the water, since we're thankfully going to us from the facility. And then I would say each ingredient, like, depending on where you're located, it might be like 360.
Yeah, so just to add on to that, so all the parts we used here, there was nothing fancy, really crazy detectors. At least we could have made it way more expensive by using the laser detector, but we straight up used a little servo, a button, and regular wiring. The only thing that would add costs to this would be the Arduinos, but that's also mass produced and we can find that easily. So while 75 is a decent price for its effectability, we can definitely keep mass producing it to what like way cheaper costs.
The solution itself is like $39 to $75, but the automated spray bottle would add that cost as well as we would hope to have this as a system throughout the mine where we have sensors that could essentially see where the dust was in the spray.
And to add on to that, we actually 3D printed a little slot where we can add it to the.
So then would you sell the solution in meter a unit, or would you sell them as two separate units so that miners who might not be able to want to transfer over to that $75 price from their free water that they had previously been using can still use the solution if they would?
Yeah, so the solution is our main product or creation of this system. So the spray bottle and the automation are essentially so it would be mainly the Great. Thank you so much.